Another indicator that the CTI might be blocked would be the presence of double potentials. So let's say we've burnt the CTI and we've got our ablation catheter sitting right on where we've burnt. So the ablation catheter is sitting on the CTI and the CTI is blocked and the ablation catheter is sitting on that line of scar that we've created. And we're pacing the proximal coronary sinus. So if we're pacing the proximal coronary sinus, that wavefront of depolarization will depolarize the tissue on the medial side of the CTI pretty quickly, because we're pacing the CS and then pretty quickly gets to the CTI. And so that will result in an EGM being detected on our ablation catheter. Then what happens is our pacing stimulus goes all the way around the atrium to depolarize the lateral aspect of the CTI. And our ablation catheter will sense that here as another EGM. So this is called a double potential, where we have an EGM here, which is an atrial signal, and then we have an EGM here, which is also an atrial signal, and then we have this isoelectric line in between. And if that isoelectric line is more than about 80 to 90 milliseconds, we can expect that this demonstrates a line of block. So widely spaced double potentials indicate a line of block, and it's for that reason. So if you had the CTI wasn't blocked, so let's say the CTI wasn't blocked, okay, what would happen is we pace the coronary sinus, and then the pacing would slowly go through the CTI because we've injured it, but it's not blocked. So it would slowly depolarize the medial tissue, slowly depolarize the tissue beneath, and then slowly depolarize the lateral tissue. But that depolarization would be continuous. So what we'd see on the EGM is medial tissue depolarizing, followed by tissue beneath, followed by lateral tissue depolarizing. So we'd get this fractionated, low amplitude, prolonged high frequency signal. It's high frequency because it's directly beneath the catheter. It's low amplitude because we've injured the myocytes and there's not a whole lot of voltage being generated. And it's prolonged because conduction velocity is slow. So this kind of EGM, if you see that on a CTI, that tells you you need to burn that EGM because it's probably not blocked. I'm perhaps overgeneralizing here, but if I see this in the lab, I 100% point this out, that this needs to be burnt or this needs to be looked at further. But if you see these nice, beautiful double potentials that are widely spaced with a lot of isoelectric line in between, then this indicates that we probably have achieved block here. And sometimes what can happen if the block is, or let's say that this gap in the CTI is at the IVC end. So let me get rid of some of this clutter. So let's say that the gap is at the IVC end. And so we've got block along the anterior and mid portion of the CTI, but we don't have block on the IVC end. So conduction is sneaking through the IVC end. What can happen is when we put our catheter here, we can have a widely spaced electrode. But when we put our catheter on the mid CTI, which is close to the gap, what happens is the double potential gets closer together, so less widely spaced. And then as we get on the gap, it becomes this kind of signal. So that's really important to know as well. So this group down the bottom here found a way to quantify the isoelectric period for double potentials. So if you've had atrial flutter and then you've terminated the atrial flutter and then you perform a CTI ablation and you get double potentials like we see in this slide here, where we have a double potential. So this is potential 1 and this is potential 2 when pacing from the coronary sinus or halo 1-2. So they're pacing from halo 1-2 in this example here. You can measure the time from the stim to the first double potential, which they call SD1, and then measure the time from the pacing stimulus to the second double potential, which they call SD2. And if you add up both of those values, so this might be 20 milliseconds and this might be 200 milliseconds, so it'll be 212 plus 20, so it'll be 232 milliseconds, that number should be at least 90% of the atrial flutter cycle length. And if that is the case, it has a 94% sensitivity and 100% specificity for CTI block in the particular data series that this group presented. So if you have widely spaced double potentials, where the stim to double potential 1 plus the stim to double potential 2 add up to 90% of the flutter cycle length, then that should indicate that the CTI is blocked. And this makes sense because if you pace from the lateral aspect of the halo catheter, the time it takes to go from here to here, plus the time it takes to go from here to here, should roughly add up to the atrial flutter cycle length, because the flutter circuit is this kind of circuit. So when the CTI is blocked, the transismus time is usually roughly double that of the pre-ablation transismus time. If it's much less than double, then start to suspect that it's not blocked. Furthermore, the chevron activation during atrial pacing will change to a more straight line activation, with halo 1-2 being the last EGM to activate. But these only indicate block, they do not prove it. The way to prove block is through a method called differential pacing. And bidirectional block using differential pacing is the procedural endpoint of CTI ablation. And this helps to reduce recurrence rates quite significantly. So this is how we do differential pacing. We have a coronary sinus catheter, and then we've got an ablation catheter. We've achieved block across the isthmus, let's say, but we don't know that. We want to prove that with differential pacing. So what we do is we place our catheter lateral to the cavotricuspid isthmus line, and we pace the coronary sinus. So we pace from here, and conduction can't travel across the line, so it needs to travel to the ablation catheter. But our ablation catheter is quite close to the line. And we measure the time from our pacing stimulus to the ablation catheter EGM, so to here. And that measures 175 milliseconds. We then place our catheter further away from the line, anatomically further away from our pacing site. But if the CTI is blocked, it's electrically closer to the pacing site. B is electrically closer to the pacing site than A, even though it's further anatomically from the pacing site, if the CTI is blocked. And so then you measure the time more when your ablation catheter is further from the line. You measure the time it takes from your pacing stimulus to the new location. So you measure from this pacing stimulus to the ablation catheter EGM, and that measures 160. So this is shorter than this. And what that indicates is conduction is occurring in this direction. It's not occurring slowly through this direction. Because if this was the case, B transismus time would be greater than A transismus time. But that's not the case here. So that's what differential pacing is. It proves that the doubling of the transismus time is not due to slow conduction through the transismus, but due to blocked conduction across the isthmus and conductions occurring around it.